to our weekly BHI colloquium. First, I wanted to mention that we decided to cancel or postpone the conference, the annual conference that was supposed to be in the middle of May because of the coronavirus. It poses an increasing risk as a function of time to both travel, going on airplanes, going to airports, staying in hotels, and also risk to the attendees of a conference that meet people from many parts of the world that allows the virus to spread more easily. And so, as you know, the APS meeting was canceled. I sent a message around about that this week, and by now I heard about 2 other conferences that were canceled, and a board meeting that was canceled. So it's very natural and very appropriate at this point to do it as a measure of caution. And we will monitor the situation, and if it improves, obviously, my expectation as a theorist is that it will get worse before it gets better. That's based on the past trends of viruses. If you look at the history, 2009, 2004, and even worse, 1918. There were, they spread exponentially at some point, and it may happen next month that it starts spreading. Instead of to 100,000 people, to millions of people. So that's the concern. So at this point, there will not be a meeting, but we will continue our activities because at the moment there is no, Harvard continues to function the way it is. There might be a point where Harvard will reach a decision to not carry on the activities, but we will see. Now, I just wanted to mention over the past week there were 2 interesting news items related to black holes. So one of them was this image of a cluster of galaxies, the Ophiuchus cluster, and where people saw a long time ago in an X-ray image, they saw sort of a front of hot gas in contact with cold gas, but most recently they used a radio observatory, LOFAR, to find that this cavity that is in the middle of the cluster is filled with radio emitting electrons. That implies that there was activity of the black hole at the center that released 10 to the 62 ergs, which is the largest explosion that we've ever noticed anywhere in the universe. So we know that there should be a supermassive black hole at the center, but now we have evidence that it erupted some time ago and released the biggest amount of energy ever released by an astrophysical source, 10 to the 62 ergs. So that's news item number 1. And then how do I move forward?
It's the other top. Yeah.
Oh, the mouse.
Huge, as Donald Trump would say.
Yeah, it's huge. And then the second
Perfect.
one is actually an anecdote. It's not of particular importance, but people were able to tell by analyzing the spectra of stars near Sagittarius A star, the center of our galaxy. They were able to tell from spectral lines, the line ratio, that the alpha, the fine structure constant, does not change in the vicinity of the black hole. That's not big news because we knew, for example, white dwarfs, they are the end result of stars like the sun, and they're the size of the Earth. So imagine taking the sun and compressing it to the size of the Earth. That's what the sun will become when it cools off. It basically is a piece of metal, and that's called the white dwarf. And this piece of metal has the mass of the sun, the radius of the Earth, therefore a very strong gravitational potential, and we've seen spectral lines from white dwarfs that follow what we expect. So the gravitational potential of a white dwarf is actually deeper than the one of the potential that the stars are probing here, but nevertheless, it's an independent test and shows that gravity doesn't change alpha, nothing unexpected. So these are the 2 items that were in the news this week about black holes. And now we have a couple of presentations. Thank you, Nicole.
Okay, so our first speaker is Mu-Tao Wang. He's visiting us from Columbia University, where he's a professor in the math department. He also served as my advisor during my time there. And he'll be speaking to us about invariance of angular momentum.
Okay, thanks for introduction. It's always a pleasure to be back at BHI. So I want to talk about this title, Invariant Notion of Angular Momentum and Null Infinity. So the goal is to describe angular momentum after gravitational radiation for far away observers at squared plus. So this is the picture I'm interested in. This is the future null infinity described. And this astronomical events here, and the far away observer that are situated at null infinity. And how do you describe angular momentum after radiation? This may not be a problem to some people, but it remains a serious problem for mathematicians like myself. So I'll talk about joint work with Pauline Chen, Jordan Keller, Yi-Kai Wang, and Xintong Yao here. So as I just mentioned, there have been several definitions and proposals for this angular momentum by various authors listed here. And in my talk, I'd like to convey to you how we actually justify the definition. In particular, I'll explain what I mean by invariance in my title, and why do we still need new definitions. Okay, so let's start with a well-known description of squared plus in terms of the boundary access coordinate system. So if your space-time permit this kind of coordinate system near squared plus, then the line segment takes the following form here. So you have coordinates UR, XA, and there are actually these metric coefficients. Okay? So here my XA coordinates range from 2 to 3, and they represent coordinates on two spheres. And we are actually interested in this so-called U slice, namely if you just set your U equal to a constant, okay, and then you can see that this is actually a null hypersurface with this induced metric. So you set all this U equal to a constant, they just vanish. Then you just have a two-dimensional induced metric, and that is an induced metric of a null hypersurface. Okay, and in this case, you can actually read off the mass just from the metric expansion of this coefficient V there. So in particular, if you just expand it in terms of inverse powers of R, then on this order, you're going to pick up a function, and this is so-called a mass aspect function. Okay, and this function here. So I like to, well, we should imagine our squared plus here as an interval product with a two-dimensional sphere. So let's just imagine this is actually an interval with a two-dimensional sphere. Okay, whereas the interval will correspond to the direction of retarded time. So this is a U direction, okay, the retarded time. Okay. So U is actually here. And I also have a angular direction. So my X here. Okay. So it's like a cylinder, but of course this is the actual picture. So I'll pick up a function here that depends on the retarded time, and also depend on the angular variable. And that is the so-called mass aspect. Okay? And this is a function defined on squared plus. And then you can actually evaluate the boundary energy by integrating this function here along a two-dimensional sphere. So that will correspond to, so in this picture here, you can see that if U is equal to a constant, this actually corresponds to a null hypersurface. And also U equal to a constant give you a cut on squared plus here, and then you can evaluate this mass aspect function. So fixing your U here and integrate the angular variable, you are going to get this quantity that is actually the boundary energy, and of course plays a very important role here. This is the mass loss formula or energy loss formula, which is first, I would say the first nonlinear theoretical verification of gravitational radiation to show that energy actually radiates away along the null direction. Okay. And also satisfy this positivity property. Okay. So this is a picture here. Okay. U equal to constant correspond to a null hypersurface. And when you move in the U direction, and the energy will radiate away along the null hypersurfaces. Okay, so this is a case of energy or mass. And in fact, you can define linear momentum in the same way. You just integrate them with respect to L equal to 1 spherical harmonics when you pick up the linear momentum. Okay. But when it comes to the definition of angular momentum, this is actually more subtle, and it actually requires a higher order expansion of the metric coefficient. And these expansions are actually determined by a hierarchy of the Einstein equation. Okay. So in particular, this will actually involve expansion of this HAP here, and also expansion of this WA here. Okay, you can see that the mass or the energy is read off from this V coefficient. Okay, and therefore, if you write down the expansion, okay, so this is your HAP metric part, and this sigma math ring here. This represent a standard round metric on a two-dimensional sphere. So again, you write down in terms of expansions of powers of R. So you're going to pick up a term here, CAB here, and always carry this U dependence and the angular dependence. Okay, and likewise a DAB here. And by the virtue of Einstein equation, you can actually solve this WA here, and this is actually this term here. Okay, and okay. So this 1 over R squared term is actually a term that is related to this CAB here. So CAB is actually a shear tensor. Okay. And then you can take you can take this divergence with respect to the angular variable, okay, and you can see that this CAB will occur here, you also occur here, and there's actually a special this is really a NA here is considered a one form or vector field, okay, and so this is a particular vector field here. And this is referred to as the angular momentum aspect. Okay, so just imagine this NA is again another geometric quantity, which is a vector field that is defined on your on square plus, as I mentioned. So it also has a U dependence and an angular dependence. Okay, and almost all existing definitions of angular momentum ascribed have this NA here as a leading term. Namely, when you talk about angular momentum, you want to pick up a rotation killing field, okay, and you want to be able to integrate against this NA here, okay, and then you integrate over a two-dimensional sphere. I mean, this is just a standard form of angular momentum that you will expect. Okay, so this NA will appear in all definition, but somehow different approaches. Okay. For example, there's a Hamiltonian approach, and you can also talk about spinner, twister approach, and a Kohner type approach, and different ways to deal with the BMS algebra. You actually lead to different definitions. So there are actually two main issues that you actually have to deal with when you give out this definition. First of all, there's this issue of referencing. I mean, you can write down an expression here, but you want to make sure that if this corresponds to the Minkowski spacetime, then your definition should be equal to 0. So you have to find a good reference term to subtract from. And secondly, because the BMS group, there's this well-known super translation ambiguity that you have to deal with. And there's also this Lorentzian ambiguity. So Lorentzian group is SO31, and where you can actually decompose into the rotation group and the boost group. But somehow it's not clear how to do this kind of decomposition when they're actually sitting in the BMS group. Okay. And there's actually another way to describe square plus. This actually results from Christodoulou Kleinerman's proof of the nonlinear stability of Minkowski space-time. Okay, so before for example, in the case of boundary access coordinates, you always start from square here, and you try to describe solution of Walken-Einstein equation near square plus. But in this case, you can really start from a Cauchy data. Okay, so this Cauchy data is very close to flat data here, and then you can actually solve the Walken-Einstein equation all the way up to a square plus. Okay, and so Ricci actually utilized this description to define angular momentum. So this angular momentum again is of this form here. Ya is a rotation Killing field, but identification of rotation Killing field is actually important here because you just have asymptotic flat space-time. How do you actually identify them? But anyway, still this form here with this there's actually a zeta A here, and this is one form that I will describe later. Okay. Recently, it's Keller, Yi-Kai Wang, and Yao. They actually compute the limits of a quantity that we discovered before. This is so-called quasi-local angular momentum in this boundary sex coordinate system. So the coordinate system actually give you a foliation of spheres. So you can actually really restrict the definition of quasi-local angular momentum along these spheres, and then you can take a limit. And you can take a limit at a cut and use it as a definition of angular momentum as quite close. Okay. And some advantage of this approach is that this definition actually relies on the following. So you take a two-dimensional sphere, correspond to a sphere here. Okay. And what you do is you have to solve this equation that was proposed by myself and Yao 10 years ago. So you have to solve the optimal isometric embedding equation. So you're going to take this surface here, and you want to pick up the intrinsic geometry, and you want to embed this surface here into the Minkowski space-time, so that I actually have exactly the same intrinsic geometry. Okay. So the approach here, we actually take care of the referencing part, because when you're doing this one here, you're basically subtracting data from the Minkowski space-time. So in particular, if your surface is already in Minkowski space-time, this procedure here will identify itself and will find the right reference. Okay, and also once you actually have embedding into the Minkowski space-time, then you can actually pull back all the Killing field in the Minkowski space-time. So in particular, you can pull back a rotation Killing field here. So you will be able to distinguish those those Killing fields that are representing a rotation, and those that represent a boost. Yes.
So you mentioned this rotation Killing field.
Right.
Are you assuming axis symmetry?
No, I'm not assuming axis symmetry at all.
Will a general space-time have a rotation Killing field?
No, they don't. They don't.
So what does this mean?
This means that I take a surface in a general space-time, and I do this optimal isometric embedding. So I'm going to find a copy of the space in Minkowski space-time. But in Minkowski space-time, I already have this Killing field. So I just transplant this Killing field back to my Minkowski space-time, back to my physical surface.
Okay, I see.
Yeah. Okay, so let me just give you a comparison of selected definitions in boundary set coordinate system. So first of all, this one given by Hawking, Perry, and Strominger. So the definition is this NA that I talk about, and minus U. U is just this function, this retarded time function, as a function on square plus. And then this M here is the mass aspect. Okay? And there's also one that is defined by Kushel, Jersky, and Kichowski. So they actually have this expression here. And there's also one given by Barnard and Trosset. So they actually have an additional term here. But this term is going to integrate away when you integrate against an angular rotation Killing field. And last, this is the one that is computed by Keller, Wang, Yao. So you can see that this term here is actually exactly the same. And this term here also appear in the definition of CJK and BT here. And this is a new term here. Okay? And this is actually quite interesting term here. On the one hand, you actually have the gradient of the mass aspect, just like in the Hawking-Parry-Strominger case. But somehow there's actually a function here, C here. And this is this function, again, it's a function defined on square plus, but actually involves some more refined structure. It turns out you can take this CAB here. CAB is a shear tensor, so it's actually a trace-free two tensor, trace-free symmetric two tensor on the two sphere. Then you can show that any this kind of two tensor admit this kind of decomposition, which is just like Hodge decomposition of closed or closed path. And then you pick up this C here that corresponds to this potential here, and then you put it here. Okay, so that's actually the only difference from other definitions. Okay, and you can see that, but in a lot of testing cases where you assume the mass aspect is actually constant, that is actually the same as other definition. But in the case when your mass can depend on angular parameter, this actually gives you a different definition of angular moment.
So does the new, more expanded definition include in some limit the older definitions? Or
Well,
what is the advantage of
that's
this?
that's why we want to find out, and that's what I'm going to explain in a few minutes. But the calculation of this one here is much more complicated. I mean, it actually consists of maybe 40 pages of calculation, because you really have to solve this equation. But it's kind of surprising that that you actually come down to this actually quite simple answer. At least you probably didn't actually expect this answer would be so simple at the very beginning. Okay. But it does involve some more refined structure of square plus. Okay. So all these definitions actually assume special space-time coordinates near square plus and compute the angular momentum associated with a u equal to constant slice. So this is a u equal to constant slice here. And I mean, in this work that we talked about, we actually define angular momentum for general non-hypersurface with the hope to remove restrictions imposed on the coordinate system or gauging earlier definitions. So for example, let me just mention, so in the case of a boundary size coordinate system, you expand this HAB in this term here, and as just mentioned, you have to assume the CAB here is actually trace-free. Okay? In fact, there's a stronger condition on the determinant of HAB that has to be satisfied. But somehow this condition, this is actually not too strong condition, but you can check even on the standard Kerr space-time. That's always the model space-time you want to check your definition of angular momentum. You cannot really find a regular boundary size coordinate system that satisfies this assumption. And there's also this DAB part. Okay, that is a next order term. And the next order term, it actually has to be proportional to this metric here. Okay. And this is so-called outgoing radiation condition. And in fact, without this condition, there might be logarithmic terms in the expansions of other metric coefficients. Because when you solve the Einstein equation here, you have this term here that will give you 1 over r on the right-hand side of the ODE. And when you integrate it, you're going to get some log term here. Okay? And this is actually considered to be, well, of course, there are physical arguments. But somehow these logarithmic terms actually contribute to different pitting properties of the work of Christopher Kleinemann. So it turns out in this work of stability of Minkowski space, when you look at how curvature decay on our infinity, in their proof, it actually exhibit a different kind of pitting properties here. And these pitting, I mean, you can actually explain this different kind of pitting come from these logarithmic terms. So in a way that, although they're unpleasant, but they actually exist. I mean, you can take a Cauchy data here, and you involve to infinity, and these logarithmic terms actually appear there. So somehow, and in fact, as I mentioned, Rizzi actually adopted this framework of Christopher Kleinemann. But in his case, he's not working in boundary size coordinate system, but in fact, he was working on this kind of gauge that chose by Christopher Kleinemann. But his definition, when you want to do the referencing, meaning that you want to make a definition vanish for the Minkowski space-time. So here's actually has an imposed gauge condition. And the gauge condition is actually equivalent to the vanishing of this C term here that I just mentioned. It actually appears in the angular momentum here. So this is the assumption that he assumed. So somehow, one hope of us is actually try to remove all these conditions on the coordinate or the gauge system. And there's actually another reason to extend this definition beyond a U equal to constant non-hyper surfaces. So this kind of even in the case of boundary exact coordinate system. Okay. In fact, you don't have to look at a U equal to constant sign. In fact, if you just take any section, okay. As I said, well, I can just write it as U is equal UX here. So I can just take any section defined by U is equal to a function of X. Okay, that represents a surface in square plus, but you can actually show that it actually extends to a unique non-hypersurface in your space-time, or at least locally. Okay. So in a way that this kind of surface will actually give you a non-hypersurface in space-time. And in this case, you can actually define a modified mass aspect function. Okay. So just minus this quarter of this double divergence of this CAB, this is shear, you recall, and this actually gives you another function in square plus. The advantage of this mass aspect function is that now you can take any section here, and then you can evaluate this integral, okay, so which is equal to this one here. And that actually gives you the mass of this particular section. So this is different section here, and you integrate this. And this term here is actually interesting. This is a double divergence. In general, you might think, well, it's integral to 0, but this is actually not true, because I'm substituting this u here by f of x here. So this is actually not the right metric when you do integration by parts. So in general, this term actually exists unless your f of x is a constant. So unless you're actually in the original case, when you're just looking at the mass of a u equal to constant slice, and you just integrate the mass aspect. And in general, you really have to consider this kind of modified mass aspect. And this expression is actually nice because in a way that it defines a mass that is equivariant with respect to the BMS group. Namely, it doesn't matter which boundary size coordinate system you have. Just tell me how you define this section, and tell me what your mass aspect function is, tell me what your CAB is, and I just write down this, and they're going to be the same. And another important property of this mass aspect function is that I mentioned the energy, the boundary energy is actually decreasing along the u direction. Okay, but you recall the energy is integral. But after you modify the mass aspect by this term here, you can show that this quantity here, this function here, is point-wise decreasing with respect to u. Okay, before it was just integral, just the integral is decreasing, but now this is a point-wise quantity. And in particular, you can actually show the following. So if I take any two sections in square plus, okay? So let's say this is actually sigma 1 here, and this is a sigma 2 here, okay? And I can really define a notion called one is the retarded future of the other one. Okay? So for example, in this case, you can see the sigma 1 is going to be in the retarded future of sigma 2. Okay? And well, they can be both quite arbitrary. They're just sections on scribe. Okay? In particular, you won't be able to represent them as constant level sets of u in a particular boundary size coordinate system. But now you can show that the mass here is always less than here. Okay? So it's really a topological statement. I mean, you can actually cook it up and then write down this integral here. Okay? So this is a good way. I mean, if you are able to extend your definition to a general surface here, then you will be able to talk about invariance, and you may be able to describe better this mass loss property. Okay, so yeah, I hope I still have like a few minutes, right? Yeah. Okay. So let me just talk about our approach. So our approach is, let's forget about space-time coordinate or space-time gauge. Let's just focus on a null hypersurface, okay? So, well, suppose we have a null hypersurface in space-time, then we say this is asymptotic flat. If there exists a coordinate system on this null hypersurface, such that if you look at the induced metric on your space-time, then you actually take the following form, okay? So you can see in particular, in the case of bounding size coordinate, if you restrict to u equal to constant slice, it is of this form. Except in the case of bounding size coordinates, you impose restrictions on this term and also on this term here. Okay? But in our case, we assume this is, they're both completely general. Okay? And this is just about a null hypersurface. But of course, in order to describe, define any quantity, you have to pick up also the extrinsic geometry of this hypersurface in space-time. And you actually rely on an extrinsic non-normal. So you need an extrinsic non-normal direction. And then we can always normalize it, so we satisfy this condition. And this will actually give us another, this is basically another second fundamental form. I'm sorry, this is actually L bar here. Okay. And this is also, this one should, yeah, I mean, we should move, this should be L bar, and this should be L. Okay. So this is really a second fundamental form with respect to this other extrinsic null direction. And this is actually a connection form. But once you have this asymptotic flat picture, you can also solve the Wagner-Einstein equation, and you'll be able to obtain the expansion of this chi AB here, zeta AB here. And because we're now assuming any conditions on these two, so you're going to get logarithmic terms. Okay, so you do the expansion. So for example, the leading term is actually this one here, but the next order term is actually something like this, and you have log terms everywhere. So this is actually the setup where we actually try to define the quasi-local angular momentum. Okay, and this is actually the answer. So assuming the linear momentum vanishes, okay, of course this is with respect to the one that we defined as the one coming from the quasi-local linear momentum. And then you can write down the answer of the limit of this quasi-local angular momentum and of this R-level set. So it actually corresponds to this quantity. Well, so the leading term here corresponds to this zeta A here. And this zeta A here is actually similar to the one that Rizzi defined. It's really this connection form and -2 coefficient. Okay, and the C here also appear. Okay, and the C here, you recall, shear will correspond to this term here. And here we do not assume this is traceless, but of course we can subtract the trace, and this is still a traceless. When traceless part is still a traceless two tensor here, and you can still perform the same decomposition, and you can pick up a C here. And this rho -2 here consists of this term here. This is the expansion of chi. And this is sigma 1. This is actually the equivalence of a shear tensor, except we don't assume it's trace-free. And in fact, the trace will actually appear here. So this is actually basically the trace term in this one here. Okay. So this is actually general. In particular, if you impose the conditions of bounding sex coordinate system, it will actually recover the expression that KWY obtained. Okay. And surprisingly, all the logarithmic terms actually vanished. So they were carried in the calculation, but when you look at the final answer, those terms that, for example, is log R divided by R squared, all these terms are actually vanished. Okay, and moreover, I just have a last page here. We actually prove several properties. Okay, so first of all, well, in all these definitions, we have a null hypersurface here. And you recall, I always assume that you actually have a coordinate R and X, A here, and you look at these surfaces here, and you define this angular momentum. Okay, so you have to choose a surface foliation in order to do the calculation. Okay, so it may be just a quantity that is associated with your foliation, but we can actually prove invariance. So turn out this is actually independent of this foliation that you choose. Okay, in the sense that you can always do O1 perturbation. Okay, order 1 perturbation, and you're still going to end up with exactly the same answer. Okay, so this is the first invariance property. You choose a foliation and you calculate this quantity here, but at the end, it doesn't really depend on the foliation. So it's really a quantity that is invariantly associated with your null hypersurface. It's about your hypersurface, not about your foliation. And secondly, we can actually specialize to the boundary size coordinate case. And therefore, you will provide an angular momentum definition for any section of this form in square plus. And it will satisfy this BMS equivariant property. Namely, it doesn't matter which boundary size coordinate system you pick up. Give me your BMS function associated with your coordinate system, and tell me how do you represent this surface, as a section in this coordinate system, and I can just write down the answer here. And and of course, what we really want is to calculate how the angular momentum change. And this is still underway, because this is actually somehow major difficult in the sense that we actually assume that the linear momentum vanishes in order to do this calculation. Okay? But in fact, this is also another reason why we want to just look at a null hypersurface. Because if we're just dealing with a null hypersurface, the problem here is that whenever you choose a frame here, you may not be in the center of mass frame, or if you just work with a boundary size coordinate system. But if you just work with individual, null hypersurface, then I can really choose a different frame, so that with respect to this null hypersurface, my quantity, they are actually in center of mass frame. Okay? But that's actually much more difficult, so there's still calculation is still ongoing. Okay? So let me just stop there. Thank you.
Just a question or two.
So this quantity that you calculated,
Yeah.
it's a scalar, right? Or does it also come with orientation?
Well, it's actually a vector field. You have to pair with a rotation killing field, or one phone you have to pair with a rotation killing field. So you still have to pair with them. Yeah. But it's just the way we pick up rotation killing field, we actually do is through this isometric embedding. So there you can distinguish those that correspond to rotation, those correspond to boost very well. I mean, there's no ambiguity.
In the Minkowski space, you mean?
No, after this, because the optimal isometric embedding is actually unique.
Okay.
So you have a unique way of pulling back those killing fields.
And so that gives you all the information, including the orientation.
Right. Yeah, in fact, if you replace the definition, if you replace the rotation killing field by boost vector field, and that will actually give you a central mass.
Okay.
So a general space-time, this is not associated to an isometry, or a rotational isometry.
No.
So what sort of problem would you envision using this definition
Okay,
for?
so I'm sorry, because I didn't have time to explain this approach of quasi-local method. So in our approach, I mean, this is really a quantity associated with two-dimensional surface in a space-time, just like a surface here. Okay, then we pick up the geometric quantity here. Basically, just involve the induced metric and the mean curvature vector. Okay, and then we can actually find a copy of this surface here in the Minkowski space. So this is actually Minkowski. This is a general space. Okay, and they actually have exactly the same intrinsic geometry. Okay, and we have a way to define an optimal isometric embedding. Basically, we write down some energy there, and we can minimize them. And this isometric embedding is basically unique. So once you have this physical data, you have a unique one here. And here you can actually compute, and then from here you can actually compute the energy momentum. So it's going to give you an energy momentum vector like this one here. And then you can look at your orthogonal one here, and that will give you the Lorentz group, or the Lorentz algebra. And now you can take each of the Lorentz algebra, and then you restrict here. Or a different way of saying this is that once you have this embedding here, you can pick up the embedding. So you have, in Minkowski space, you actually have 4 components. Okay? So this is each one of them will give you a function. And you remember how to write down the killing fields in Minkowski space. Now just take those expressions here, replace each of the coordinate by these coordinate functions. And there's a unique way of doing this.
Yeah, I understood that. I was just asking if you don't have a conserved quantity, why are you trying to define an angular momentum? What do you want to use an angular momentum for?
Well, what do I want to use for angular momentum? Well, if there's something here, some astronomical event here, I want to see how they rotate. And I want to be able, I want to measure how it rotates. So I want to define angular momentum.
Do you know how this version of angular momentum would respond to like a super rotation compared to the other ones?
Yeah, we know how it behaves under super rotation. There's a formula. You can write down the formula very explicitly. Yeah.
So
Yeah.
what's the qualitative difference?
You mean this one here with respect to other one?
Yeah.
Yeah. This NA power is the same because each one of them carry this NA power here. But this new one actually has some this new term here. Yeah, this actually gives you some new information. And you can compute how this transform under different super translation. Basically, what happened is that you have this one here and you compute the potential, right? Okay. But what you can do is you can actually take this potential here. This potential again depends on this u variable and x variable here. But now you really have to specialize to this section. So you have to replace the u by f of x. So this is basically how you actually transform. Yeah. And also I forgot to mention in this definition of angular momentum. In fact, our definition actually involve the new one will actually involve the first derivative of the defining section, okay? And this is actually expected because the ambiguity in BMS group. You really have to know the tangent space of your section in order to pick up a rotation field.
I think we better move on. So let's thank Mu-Tao one more time first.
Jose, you want to plug in? So while Jose gets set up, I'll take the time to introduce him. Jose Gómez got his degrees in astrophysics in Barcelona and Granada, which I guess are part of Andalucía. Is that that correctly?
That's the region
which
of
is
Spain.
which is a lovely region of Spain. He spent a year or two at Boston University.
About 3.
3 years. Okay, working with Alan and Svetlana, who are in the audience, and he was a research fellow there on a Fulbright scholarship. He's interested in relativistic jets from black holes, and is a colleague of mine and other people on the Event Horizon Telescope. And I guess the Event Horizon Telescope makes him very well equipped to give us the sharpest views of blazar jets, which is what he's going to tell us about today. So thank you, Jose.
Thank you very much, Jonathan. So thank you very much for the invitation to give a seminar here. It's always a pleasure to come back to Boston to see so many good friends. And I see you have even arranged for really warm weather. It's 18 degrees.
Just for you.
Just for me. I see that. Yeah. You knew I was coming from Spain, so you didn't want me to feel uncomfortable. Okay, so as Jonathan mentioned, I'm going to talk about how we can get the highest angular resolution observations of blazar jets. So as you know, blazars are really high powerful, very powerful relativistic jets that are produced from the creation of material onto supermassive black holes, as it is shown in this animation made by Wolf and Stefan. These jets radiate across the whole electromagnetic spectrum, and from time to time you will see time variability with new features moving around along the jet and also interacting with the standing components in the jet and so on. So the current picture we have now of this AGN is that we have the accretion disk, which is emitting mainly at X-rays. Then we have the VLR clouds. We have the jet. We have these superluminal components that are, they're responsible for most of the variability that we see in sources, in the sources that are radio wavelengths. And you see here also a strong feature that we call the VLBI core. So these jets are highly stratified, so they radiate and then therefore they cool down, and so when you move high in energy, you move closer to the black hole. And with the VLBI techniques, we have been able to image this radio part that is mainly emitting at centimeter wavelengths with VLBI arrays. And we have been doing this for decades. So since the beginning of the VLBA in 1995, there has been a significant amount of effort to try to image these sources in this regime, centimeter wavelength. So there has been, you can see here, the typical movie of one of these sources, in this case, a well-known radio galaxy, 3C120, and from programs like the one that Alan and Svetlana are running in BU and the Mojave program, we have been studying this, as I said, for decades. We have estimated that these are highly collimated sources with Lorentz factors of the order of 10, always seeing a very small viewing angle, so that we have boosted emission in radio, and we know that they are in this partial scale region, they are kinetically dominated and also have a magnetic field which is partially oriented. So in observations for multi-wavelength observation, actually one of the first multi-wavelength observation by Alan and Svetlana and collaborators, they combined high energy emission X-rays coming from the disk and radio imaging of the jet, and for the first time it was established that these sources actually are generated from this mass accretion onto the supermassive black hole, and that the VLBI core may be a recollimation shock that is actually parsec away from the central engine. Further multi-wavelength observations have been showing, especially after the launch of Fermi, that sometimes in these sources we see really strong flaring events that can be seen across the whole magnetic spectrum. And in many of these cases, it seems that they are produced from the interaction of moving shocks associated with these blobs that you are seeing here with a standing feature, which may actually correspond to the VLBI core. And a very important number here is with the distance, this seems to be located with respect to the central black hole. And we have observed this in quite a significant number of sources, that this apparent recollimation shock associated with the VLBI core is located at around 10 to the 5 to 10 to the 4 Schwarzschild radii, which corresponds to about 1 parsec, give or take, depending on the redshift of the source. So this is the current picture we have now, and as I said, our angular resolution cannot resolve beyond, cannot get deeper into the innermost part of the jet, and we know that this is the area where we should have the acceleration and collimation of the jet. So for the last 3 decades, we've been observing this. We could not get a glimpse of this, because we did not have enough angular resolution. And this is obviously the most interesting part. This is where everything is, is taking place, where we have the acceleration, the collimation of the jet actual jet production, the emission of the high energy, and so on. And we know that this should be most probably magnetically launched. And we believe that helical magnetic fields should play a very important role into the jet formation. These magnetic fields can be anchored in the black hole ergosphere and Black-Snellick process, or in the integration disk in the Black-Frank pane, or a combination of the two. In fact, some of the recent observations from the space VLBI emission radioisotope I'm going to talk in a minute. This is a beautiful image obtained by Gabriele Giovannini and Tuomas Savolainen and collaborators, and you can see here we are zooming really into the core area. This is just tens of Schwarzschild radii from the central black hole, and you can see there is a very, very broad jet. So this suggests that actually we may have a combination of the two effects. And as you know, for the M87 observations, EHT observations of the black hole in M87, there seems to be a good indication that most probably Black-Snellick. So
could I ask,
yes.
What is the VLBI core? Is it some physical thing, or just the base of the?
That's an excellent question. That's an excellent question. For many years, we thought that was just the beginning of the jet. We thought that it was co-located with the black hole, but the more recent observations suggest that the upstream end of the radio jet is not coincident with the black hole. Actually, maybe like 10 to the 5 Schwarzschild radii apart. And it may be associated with a rebrightening, high particle acceleration perhaps being produced in a recollimation shock. This is indeed a very key point. So, as was mentioned before, so we believe these are these two mechanisms, and starting in 2010, and some recent GRMHD simulations, and I think this is probably one of the first by Sasha Chekhovskoy, it was for the very first time, it was possible to reproduce the formation of this jet just from very basic principle, just assuming that you have a magnetically arrested accretion disk, and this naturally launches a very powerful jet with a very high efficiency, actually more than 100%. So you get more than what you put in. So this is a good indication that we are tapping the spin of the black hole to produce these amazingly powerful relativistic jets. So we believe then that in this area there should be the jet should be magnetically launched. We do expect helical magnetic fields, and we do expect that the jet is point influx dominated. So how do we observe this region that up to now was almost impossible, and what are the main questions we are facing? I think that these are some of the most fundamental questions that we have been trying to address for more than 40 years, I would say now. One of them is, of course, what is the magnetic launching? What is this transition between the point influx to kinetically dominated? Is perhaps the VLBI core, this transition, as we were discussing before? What determines also the accretion rate and the jet power? So we have very powerful jet. We have a beautiful jet in the mid-7, but we don't have apparently any jet in Sag A. So we still do not know. It is quite embarrassing, but still we don't know what is going on here. And we don't even know what is the jet composition. We don't even know how particles are accelerated and maintained through parsec and even kiloparsec scales from the central black hole. And we do not know what is the high energy emission, where and how it is produced. So these are very fundamental questions, and all this takes place in this region which was hidden from the previous centimeter wavelength observation. So to probe this, what we need is we need this leap forward in angular resolution. We need a polarimetric millimeter in space VLBI observation, probing these scales within the 10 to the 4th Schwarzschild radii. So how do we do this? So with VLBI, there's two basic options. It's quite simple. So either you just observe an even shorter wavelength, and this is why the Event Horizon Telescope was built, so to get the highest angular resolution possible. And we have also other millimeter wavelength arrays like GMPA that nowadays also observed together with phase ALMA. And the other option is we increase our baseline. But in order to do so, what we need is actually we need to launch an antenna in space and increase our baseline and increase this angular resolution. Or even better, why not combining the two options? Why not going through millimeter wavelength observation on the ground, combining with the space VLBI, you get the highest possible angular resolution at different frequencies, and that is what magic happens, because you have information of the radiation at different frequencies and similar angular scales. So you can actually start deciphering what are these mechanisms. I'm sorry?
As long as it's not optically thick and there is emission.
Exactly, that's an excellent point, and this is one of the main issues with radioastronauts, I will say. So radioastron, this was actually a Russian-led space VLBI mission. This was the continuation of the Japanese VSOP mission. It was launched in 2011. It is a 10-meter orbiting antenna with an apogee almost all the way to the distance to the moon. So theoretically, at the highest frequencies or shorter wavelengths that it is observing, or it wants observing 1.3 centimeter, we can in principle achieve an angular resolution of just 7 microarcseconds, actually. And it had to do a receiver for polarization observations at 18 and 1.3 centimeter. And unfortunately, the mission was ended in 2019, last year, because there was some failure in the communicating antenna. Nevertheless, we we have been carrying out a key science project for observing this blazar with a radioastron that started since early science, and in fact accounted for about 70% of all the imaging observations that were performed with 379. You can see here a list of the different sources. You can see here your more particular one that you may be interested in. So we have quite a number of them. Obviously, the most powerful sources which provide the best data. And the main goal of this key science project was to actually determine what is the jet formation mechanism in these very powerful sources. And starting with the first observations in 2017, the first participation of phase ALMA in VLBI observations, we started combining our radioastron space VLBI observations with millimeter VLBI observation on the ground, as I mentioned before, to get this indication of how the emission is changing with frequency when we observe a very similar angular resolution. And I'm going to present just a brief overview of some of the results that we have obtained. Let me first start with one of the first observations we made of BLAC. We observed at K-band, that is 1.3 centimeter, with a bunch of term antennas, and you can see here the UV coverage. These are the location of the different antennas during our VLBI experiment. You can guess what is this, and this is a radioastron. So this, you can see, the orbit of the radioastron, it's not particularly good for imaging, and so we have a UV coverage that in some cases, is basically one-dimensional. In other cases, we get a better UV coverage. You can see here the visibilities we obtain, and in amplitude and phase. And these are one of the first images we obtained with radioastron, also in polarization. This is with what we call a natural weighting, which downweights a little bit the visibility, the information to the space VLBI antenna. But you can see here the jet we obtained with an angular resolution of 1.3 centimeter of 100 microseconds. And when you give a little bit more weight to the ground space VLBI antennas, then you can see that we started to get quite amazing angular resolution. This already 30 microseconds. So the highest angular resolution before was 50 microseconds before these observations. And if you push a little bit the weight of the visibilities to the space VLBI, then we got this image with an angular resolution quite similar to what the EHT is actually getting, 20 microseconds. And you can see that we were able to resolve the jet and also determine the polarization. And we were probing, in this case, the magnetic field at a distance of about just 1,500 Schwarzschild radii from the center black hole. We also combined our observations with ground-based observations, and we produced Faraday rotation synthesis images. And you can see here, this is the image in colors showing the rotation measurement. The contours shows total intensity, and these are two-dimensional histograms of the rotation measurement and the EVPAs, and focus on this core area. So this is the tricky part. This is the place where we want to investigate what is the configuration of the magnetic field. And if you can see here, there is a clear, if you move around the position of the centroid of the core, you can see that there is a clear trend in the variability of the rotation measurement and of the EVPAs as you move around the position of the central black hole. So, and this is quite in good agreement with numerical simulations, that show that indeed this is what we should be expecting. That if we have that further rotation changes, it's a good indication that we had a helical magnetic field threading the innermost part of BLAC, and this is why it is triggering the jet formation. So let me now move to observations of another well-known source, 3C273. In this case, we made observations at 18 centimeter, and this is the UV coverage that we obtained. And in this case, we obtained fringes up to a projected baseline distance of about 5 Earth diameters, and we got an angular resolution of about 0.8 milliseconds at 18 centimeters. So this is the highest angular resolution at this observed frequency obtained so far. And this is the image obtained by Gabriele Bruni and collaborators, and you can see here that we have resolved the jet in 3C273, and you can see that there is an initial jet, and then there seems to be like a limb brining in the jet. Actually, when you compare this with the Mojave data in contours, now you see the stacking of more than 30 years of observation of 15 gigahertz. And you can see that the colors which indicate our radio astronomy observation show a clear limb brightness. So the jet edges are brighter at 18 centimeter than what we see on the ground at 15 gigahertz. And also, we combine these observations with higher frequency observations. In this case, 5 gigahertz observations made by Laura Garcia and collaborators. And this is the radio astronomy image at 5 gigahertz. And now you can see there are some clear differences between 5 and 18 centimeter. And in fact, if you put the two images on top of each other, this is what you get. Colors is 5 gigahertz, as mentioned here. Contours is the 1.6 gigahertz. And you can see that we see like two different jets. And this is an indication of a really very strong stratification in particle energy density and perhaps a magnetic field in 3C273. This is the first time we have seen this. So this is telling us also that there should be this strong stratification, and perhaps this is also due to the presence of a helical magnetic field threatening the jet in 3C273. Then let me now move to OJ27. For those of you that are not familiar with this source, OJ27 became a little bit very famous because it was observed that every 12 years we will see a flare in the optical. So it was like a clock. Every 12 years, a flare with a double peak, and that was associated with perhaps the presence of a binary system. So it's been modeled by Marty Valtonen and collaborators, and they claim that this double peaks flare in the optical that we see every 12 years is produced by the fact that we have a binary with a huge primary of about 140 million solar masses. This is one of the largest black holes, and actually I think this is quite difficult to get something more massive than this for a black hole. And so they claim that these flares are produced when the secondary crosses the accretion disk of the primary, and this produces enhanced emission in the optical, and this leads to this double flare. Actually, they had been able to predict when the flares in the optical should take place in astonishingly enough. It seems to be right. So this may be actually one of the best cases for a binary black hole system, and keep in mind that this is a really tiny system. The separation between the two of them is just basically 0.1 parsec or 26 microseconds. So they are basically touching each other. This is a sub-parsec binary black hole system. The best system, the best candidate we have for this sub-parsec binary black hole system, which of course will be very, very interesting once we have LISA and gravitational wave from the space that could detect actually this emission.
Expect to move the jet base across this.
Excellent point. Exactly.
And can't you look for them?
Exactly. So all my next transparencies are to discuss it.
Does the secondary have its own accretion?
That's an excellent point. So they should have another accretion, and perhaps there should be even a secondary jet coming out of there when the secondary crosses the disk of the primary. So this is another option that we may see actually that as well. So in this plot you can see that this is a very well established source. I mean, this is a really, it's really bright in centimeter millimeters, so it's being observed extensively. And you can see here, for instance, the evolution of the jet, of the direction of the jet with time. So this is the change in the jet duration since 1995, since the beginning of the VLBA. And this is this has been put together by Mash and Cohen, analyzing the Mojave data. And here you have also what is the position angle of the jet as a function of time. And these are, the data are the green dots. And you can see here the binary black hole model put by Marty Valtonen and collaborators. So definitely a very interesting source. So we took a look with radio astronomy, and we were really lucky.
About 5
minutes.
5 minutes to talk, and then 5 minutes.
Okay, I'm going to rush a little bit. So these are the radio astronomy observations. We were very lucky. We observed at 15 Earth diameters. So huge baselines. This is UV coverage, and these are the images we obtained. And again, with different weightings. So when we use the maximum weighting to the space of the antenna, this is the image we got. we got an image with an angular resolution of about 10 microseconds, which corresponds to about 20 spatial radii for the huge burning black hole. And if you see, the orientation of the jet actually seems to be changing with angular resolution. The deeper you look, the more bent it is, which is actually what you would expect for the case of the planetary black hole system. But I think you were actually yesterday commenting about which one of these is Ramesh. You asked which one is the core. Actually, we have no idea. It is a bit embarrassing, but we do not. So for this, we need spectral index information. We need, and then here's when, you know, combining similar angular resolution with vastly different frequencies, where we can get the answer. And this is why we put together a campaign. So we put together a campaign that has been running since 2017, combining the first EHD, GMDA plus ALMA, and radio astro observation. And I'm going to give you just a flavor of this. So this is the 3 millimeter observations that we made. This is GMDA plus ALMA, and this is the previous radio astro observations, 3 years apart, similar structure for the jet, but look at the position angle. So we notice that in 3 years there seems to be a clockwise rotation of about 60 degrees in the orientation of the jet. And we kept observing with the GMBA. So, and this is the 2018 observations, and you can see here, so a slight rotation, but in this case was clockwise, and in this case is counterclockwise, and 2019 again. So when we compare the different images, we see that apparently it was clockwise rotating, and then counterclockwise rotated, which is quite in agreement with the binary black hole system. So really quite nice. So let me now move to another very interesting source, which is 3-79. These are the radio astro observation. This is the image from Svetlana and Alan. This is the beautiful laser image, 7 millimeter, and this is our radio astro image at the same angular resolution as the VLDA. So you can see quite very similar structures. But what happens when you put your glasses from radio astro glasses and you zoom in into the jet? When you zoom in all the way with the angular resolution that a radio astro provides, then, you know, magic starts happening, and then you start resolving all the different structures in the jet. And this is the actual radio astro image with the actual 30 microsecond resolution. And Ramesh, I think you will be interested in this. They look like filaments. It's quite amazing. So we were really quite shocked when we saw this. And actually, Tuomas Savolainen and collaborators also got from imaging of ML7, this is 18 centimeter, but look at this. Don't they look also like a bit of filaments? Look at this, Ramesh. I think we need to talk about this. Exactly. It looks like that. And seems to be getting similar thing with this 79, so really quite astonishing. And this is a beautiful EHD image we obtained, and has been submitted by Jung Kim and the rest of the EHD collaboration. And you can see here how they compare. Again, beautiful, very similar resolution, completely different frequencies. Do you see similarities? So this is the core, and this is this innermost component. So they look quite alike, and this is actually an elongated core, which is, you know, it's still, we don't have a very good idea what is going on here. We have different options. We think this may be a core, and then some funny motion here. But what happened when you compare the two images? Ramesh, can you see differences? 3 years apart.
Yeah, the orientation.
You see? So this is, we see the same elongated core structure, but at different orientations. So it does seem that at these scales, these jets are almost pointing towards you, and just, you know, that slightly change the orientation and projection is quite large. And yet, this is just my last observations. In this case, 33454.3, which is a very interesting source, and you know, and we did observations. So this is by the way, this is all done by my student Antonio Fuentes in Granada, Spain. And again, here we compare our images. This is from Alan and Svetlana. This is the view images at 7 millimeter, and this is the radio astro data convolved with the same angular resolution. Now you can see some differences, don't you? Look at the core. Here is where you do see the opacity effect. So this is highly opaque and highly absorbed in radio astro, but we still see this, which is a really bright feature. Now again, we put our radio astro glasses, and then we zoom in all the way to the inner jet with the angular resolution that radiation provides, and then you start seeing that this is the actual radiation image. So this structure is being resolved out, and this is the core. The jet goes that way, and look at this.
Is this also helix?
Looks like a ring.
Yeah, look at this. And this is a very, very strong like shock. I mean, the jet goes this way, and this is right in, you know, like a very strong plane perpendicular shock. And then some features down here. I'm not sure if the jet is going like this, or this is a very
It looks
shock.
like it is helical.
Or perhaps it's doing something like
It goes,
this.
it goes in different directions at different times.
Yeah. So we actually have a second epoch of 3279, which will be really interesting to compare. Okay, so I think I'm going to stop here. So this is just a summary of the things, and I'm open to questions. So thank you very much.
Okay, so you're actually right on time. A good 5 minutes for questions, so fire away. I guess Ramesh, go ahead.
So on OJ287, right? So you showed a whole series of images with the jet
Yes.
flopping around.
Yes.
I think the first two, 2014 and 2017,
Yes.
the optical flare was between those two, right? 2016 was the flare.
Yeah, exactly. It wasn't the system.
And that was when we had a big change in angle. So at
Exactly.
the flare, it probably changed.
Exactly. And that was, Ramesh, that was when the jet started to go the other way around.
Right,
And in fact, I think this is the image.
right.
In fact, there was a TV flare, actually, right here. So in 2017. So please go here, Ramesh.
Right.
Yeah.
I was just thinking, between these two, there's a big change,
Yes.
angle. Then it is slowly recovering.
Yes.
This big change probably was caused by that flare episode, when the second black hole came very close.
Exactly. Exactly. This is exactly what we think. In fact, we proposed for 2017 because we knew there were to be a flare, and we actually caught that.
So 12 years after that, you must be sure, please take lots of pictures
Yes,
during the flare, and
Exactly.
let's see what this guy is
Exactly.
So
doing.
that's
exactly.
2029.
27, it's right.
So Adi, do you have a question?
Well, it seems to me that we're playing here with a few times the Earth radius, but why not put something on the Moon itself?
Yeah.
I mean, now that there is talk about going back to the Moon.
Yeah. Actually, that was my last time spending it, but I thought I was actually running out of time, so I escaped
Well,
it
why don't
back.
you show it now?
Well, I can mention to you, it's, the Russians are now leading a second space failure mission. In this case, they are going all the way to millimeter wavelength, all the way to terahertz. And the idea is to put it in L2. Whoa.
Oh.
And this is going to be huge, and I think Michael is going to be particularly interested in that.
I'm going to go on the spacecraft.
Yeah, it's in L2, so we may be able to see the star rings. Perhaps Michael may want to come here because he
But there
wrote
will be
a
an issue
beautiful
with
paper.
brightness. I mean, even
Yeah.
though you have the angular resolution, you need it to be bright enough so that you can see something.
Exactly.
So
This
that
is
will be the
the-
issue.
Yeah.
Yeah, so that's the millimetron.
That's a
mission,
millimeter mission. Actually, it is actually funded. So the Russians are, very serious about this, especially after the HT observations. So for them now it's a very interesting case. So the idea is to move it to L2, do the single disk observation they want, and then to bring it back to Earth, and then do a space LDI together with the EHT.
But my question, if you put it L2,
Yes.
what is the brightness temperature that you need in order to see enough photons?
Exactly.
What is it? Is it 10 to the 14 Kelvin?
Exactly.
Is it 10 to the 20
This is an-
Kelvin?
This is an excellent
No, but that's a
point.
simple question. I mean, you can answer it just on the back
Yeah,
of the head.
it's
So what's
around
the answer?
it's around 10 to the 14.
10 to the 14.
10 to the 14, but this has been actually observed with radiation. One of the main programs of
But 10 to the
radiation.
14, you need the stimulated emission. Because
we-
10 to the 12 is the limit.
Exactly.
I mean,
We don't know.
But times
But you
Doppler
can have
factor.
Doppler
We-
beaming.
By how
Exactly.
much?
It could be 10, 100. So we don't know how much it is.
Okay, so you're on the borderline.
Exactly.
Yeah.
So this is a very good point. It has been observed. Actually, one of the main scientific reasons of radiation was to measure brightness temperature. This was Kardashev dream, and it has been detected 10 to the 14. But as Alan mentioned, I mean, this is actually to the what is the Doppler factor. So if we have 100
So we have to be lucky.
Yeah.
So also you can get projected baselines that are shorter than that, depending on where it is in the sky compared with the L2 to Earth
Yes.
baseline.
My feeling is that for L2, I mean, it may be able to get some detection. I don't think we are going to do any imaging. If we put in L2, I mean, there's not going to be any imaging, but Michael wrote this beautiful paper about the possibility of using these extremely long baselines to detect sub-rings in M87. And that's going to be huge. I think that has...
Does it have enough brightness?
Michael, do you want to comment at all?
The answer is yes. It does have enough brightness. Right? I mean, it's not just about compactness, but it's also about flux density. And the black hole is giving you arbitrarily sharp features. So this is something where I would say there was nothing before in nature where we would expect to be able to observe these things. Black holes give us this gift, this thing on the sky that's perfect for these extremely long baselines.
Yeah, but when you say the black hole, it's not the black hole, it's the electrons that give you the brightness temperature, and there is a limit on how bright the electrons can be because of pair creation, the catastrophe.
That's right. That's why you need, it's a mix of sensitivity, but the black hole is giving you the increasingly sharp structures from lensing.
The brightness temperature depends on the flux, but also how tiny the emitting region it is. And for black holes, it's so tiny, it's as tiny as you could ever imagine, because we are going to see sub-rings. Those sub-rings are going to have a huge brightness temperature because they are really small, really extremely small.
But each successive ring gets...
Exactly.
Lensing doesn't change brightness.
I know, but an interferometer...
No, but
let's give an opportunity for someone else to ask a final question. Somebody from the back of the room, if they want to. Sorry, I don't want to put you guys on the spot. I have a bunch of questions I'll say. Well, I'll actually mention that we have another path to L2 that we were investigating, which is to piggyback onto the Origin Space Telescope that's selected. And there's actually a Astro 2020 white paper about that, which I believe Don in the back of the room.
Which will go sooner?
Oh, so neither is certain to go.
Okay, but assuming that they get what they want.
And then I don't know the answer. Probably Millimetron is more advanced.
Millimetron is expected to be launched in 2029.
Yeah. So that's far before. I would
before
say.
Origins?
I would think yes.
Origins is 2035, but
Oh,
Millimetron's been promising 5 years away since 2005.
Origins, I believe, is one of 3 proposed great observatories and is yet to be selected as the preferred one. So I think it's all very speculative. The baseline length, by the way, the full and not the projected, is 1 million kilometers. Is that right?
Yeah.
Which I don't know. I was pretty darn skeptical of producing anything at all. But Michael seems to know better. So any other questions? Okay, Jose, great talk. Thank you. Thank you again. And, thank you to our speakers.